Okay, today we're going to talk about specifically ionic bonding. And so we're going to talk about the atoms gaining and losing electrons, a little bit of review. We're going to talk about what exactly ionic bonds are, and then talk about the structures and some of the properties. All right, so if we remember from our previous video, ions themselves are a charged atom, which is when you take an atom and you either add or remove electrons. Cations being positive ions, when we lose or we take away, we remove electrons, and anions being negative from gaining electrons. Now, there are two different types of ions, two different classes, broad classes of ions. We're going to talk about monoatomic and polyatomic ions. And so monoatomic are what we're going to see to start out with, which are they consist of a single atom. They're either positive or negative. So a sodium atom that loses an electron, a nitrogen atom that gains some electrons. Those are monoatomic, one atom ions. There's also polyatomic ions, which would be a tightly bound group of atoms that shares a charge, and that behaves as one unit. So no matter what we have, a monoatomic or a polyatomic, that ion will behave as a singular unit. Some examples of the polyatomic ions are ammonium, which is our NH4 plus, or a phosphate, a sulfate, sulfite. Some of these that you've heard or you'll get familiar with. All right. So when we're talking about bonds, there's a few different types of bonds. There is ionic bonding, covalent bonding, and metallic bonding. Today we're going to talk about ionic bonding. And a bond is just simply defined as a force that holds groups of two or more atoms together. It makes them behave as a unit as opposed to individual. So we're going to start by talking about, well, how do we tell these things apart? Well, first, ionic bonds are generally going to be between a metal and a non-metal. When we get into the polyatomics, sometimes that's not true. Sometimes, like if we have an ammonium ion, that usually takes the place of the metal, and there are no metals within that ammonium. But if we have two singular ions, right, two monoatomic ions, one will be a metal, one will be a non-metal, and that'll be an ionic bond. Covalent bonding, which we'll get into later, will be two or more non-metals, and the metallic bonding is between metals. And so we start off wondering, well, how do we tell these things apart? Or what causes it to do one type of bonding over the other? And what we're going to talk about is the concept of electronegativity, because that's going to help us discern this. So electronegativity is the relative ability of an atom to attract shared electrons to itself. And so we give this a number scale, which goes up to 4, and it's relative. You compare one value to the other. So when we look at fluorine up here on the right being a 4.0 and oxygen right next to it being a 3.5, we can know that fluorine is more electronegative, or it will attract electrons more to itself. And specifically when we're talking about shared, so if two atoms, the two elements are sharing electrons, it'll pull more towards one or the other based on this electronegativity, the ability to attract electrons to yourself. Think of that like your electron magnet. The higher this number, the bigger this number here, the more you pull in those electrons with your magnet. All right. And as we look at these numbers, what we can notice is that there's a trend, right? The trend goes, it increases going up and to the right. All right. It increases from bottom to top and left to right, which again, like our ionization energy, is opposite sides, which makes perfect sense because the thing that attracts these electrons is that positive nucleus. And so the smaller the atom, the more it can pull the electrons towards itself. All right. And so if we look at these values, if we use the values here on the, the periodic table, but the electronegativity chart, all right, we can determine what type of bonds we have. And so if the difference is 0 to 0.4, it's going to be a covalent bond. We're going to get to that later. If it's a 0.5 to a 1.9, we're going to have a polar covalent bond, which again, we'll get to later. But if it is above that, if the difference is above a 1.9, it's going to be an ionic bond. And so we can see here, so if it's fluorine bound to aluminum, that is a 2.5 difference. Well, that will mean that it's going to be a ionic bond. It's bigger than 1.9. All right, so when we talk about an ionic bond, our definition for it's going to be an electrostatic force of attraction between a cation and anion. Essentially, with this transfer of electrons, we've made an anion, we've made a cation. Cations are positive, anions are negative, and those things are going to get pulled together like a magnet. Electrostatic. Think about that concept of like static electricity pulling things together, or that balloon that's pulling your hair towards it, right? This static connection. And so that's what happens. And you can see that in this image down here where there's going to be a transfer of electrons. See, there it is. It goes over here. Now this becomes negative. This becomes positive. That transfer causes them to now have a charge and they're attracted to each other, thus forming this ionic bond, this magnetic pull together. And so again, it occurs when one atom loses an electron, one atom gains one. All right. And so let's take a look at how this could work. So as we are looking at our example here of calcium plus nitrogen goes to form calcium nitride, we can look at the different things here to evaluate this reaction. And so the first thing we're going to do is look at these atoms. Well, we have two atoms here that we're talking about. We have calcium and we have nitrogen. And so we're going to go ahead and look at this. So we're going to look at the valence electrons. Well, calcium is in group 2. So we know it's going to have 2 valence electrons. Well, it's a metal with 2 valence electrons. So when you look at it, it's going to want to lose the electrons, right? It's going to want to lose both of those electrons. That's that octet rule, right? It only has 2. It's easier to lose 2 than to try to get up to that next 8. All right, so it's going to lose 2, and we're going to form an ion, which is calcium Ca, but it's going to have now a 2+ charge because it's lost 2 electrons. Now nitrogen in turn is going to have 5 valence electrons because it's in group 5. Well, it's not going to lose. It's a non-metal. It wants to gain. It wants to get up to 8. To do that, it needs to gain 3. And so when it becomes an ion, it'll become N3-. Okay? And so now we have, in general, what's going on. We have our electrons transferred. We have our ions formed. These two things can now form that bond, that connection to become a compound. Okay, so what exactly is an ionic compound? Well, ionic compounds are going to be compounds composed of cations and anions. Okay, essentially, once you have this electron transfer, there's going to be a compound formed. And so what happens is, although there are these negative anions and these positive cations, they're going to come together to balance each other out, to neutralize. and that's what forms that compound. So the total charge of the compound is going to be neutral, which means that the total positive and the total negative have to even out. All right. Now, when we show this, we represent it with a chemical formula, which for ionic compounds is called a formula unit. So chemical formulas in general show the number of atoms of each element present in a compound. In ionic compounds, because it becomes a ratio, which we're going to see, okay, because it does that, it's the smallest whole number ratio. And so if we look at a few examples, table salt will be sodium chloride. Your baking soda will be sodium hydrogen carbonate, okay? Or your general sodium bicarbonate. And then we have Epsom salts being magnesium sulfate, all right? And so how we write this? Well, we're going to need the lowest whole number ratio of those ions. So when we looked at this, okay, and we had these, we want to make now the lowest whole number ratio. Well, how can this balance out? Well, if you have this positive 2 charge and this negative 3, all right, I don't know what happened to our negative, but there it is, negative 3. What's going to happen is they have to balance out. So we'll start off and say, well, we have this thing here, a 2 plus. That's a calcium. And next to it, we have this 3 minus. Well, do they cancel out? No, clearly there's more negative. So we have to add another calcium. It'll be another 2 plus. Well, now our total positive is 4 plus, and our total negative is only 3 minus. We need more negative now, right? Because there's 3 negatives and 4 positives. So we add another negative, 3 minus. Now we have 6 total negative, but only 4 positive. So we have to add another calcium, in which case it'll now be 6 positives, 2 of these negatives, which make it 6 negative, and they cancel out. So our formula here will be, well, there are 3 calciums, Ca3, right? 1, 2, 3, and 2 nitrogens, 1, 2, so it'll be N2. And this is now our formula unit. But there's an easier way to do this, and that is the cross method. So what we can do is instead just cross the 2 charges. So with right here we have gallium 3 plus and fluorine 1 minus. We can cross them. That 1 comes down to the gallium. We don't have to write it. And the 3 comes down to the fluorine, right? Ga1F3. Let's see if it works for our nitrogens, right? Let's find out. Well, here it is. So what if we just crossed them? Well, if we took Ca, let's put it down here, Ca 2 plus and N 3 minus, and you crossed them, what do you get? Well, you get Ca3 N2. There we go. Now, the only time you have to do another step is in the case it comes out like this. Well, what if we had a lead, which is 4 plus, and an oxygen, which is 2 minus, and you cross them, so you get Pb2O4. Well, is that the lowest whole number ratio, 2 to 4? No, you would need to change this into Pb1, which we don't write, O2. And now this would be our lowest whole number ratio, okay? So anytime you have it where you can reduce it, you have to. But other than that, this cross rule is perfect, works all the time. All right, so now let's just do a couple properties, and then we'll be done with ionic bonding. So the cool thing about ionic bonding is it takes on this crystalline structure, which is really just because it's ionic and you have this connection. So what we mean by that is that when you do this thing, it takes on a positive, negative, positive, negative, positive, negative. This lattice-like look, okay? Positive, negative, positive. And this will just keep going on, okay, which is a crystalline structure. And the composition of crystals is very, very structured. Again, positive, negative, positive, negative. It's very structured. And this is why crystals are clear. Because they're so structured, light can pass through it unobstructed. All right. Some of the other properties, because of this crazy ordering, we get that these things have high melting points. They're so stuck together, guys, that the energy needed to break them apart is crazy, crazy hot. All right. And the solutions of ions can conduct an electric current. So if you're able to put salt in water and dissolve it, then it will conduct electric current. Also, if you can get it hot enough, we call it molten, right? Like lava, that will also conduct electricity. So ionic bonds, ionic compounds, will have a high melting point, but if you do melt them, they'll conduct electricity. And if you can dissolve them in water, they will also conduct electricity. All right. That's about all we need to know for right now about ionic bonding.